Reinhardt and I were told at around, I think, lunchtime that we were supposed to get together and figure out what to do with this last half hour of the day when everybody's very, very tired. We've had a huge range of topics, and Reinhardt and I, during lunch, were already beginning to discuss all kinds of things. We agreed that we should not be the ones discussing and debating, etc., and rather we would like the audience to participate. And I think Reinhardt and I discussed some possible topics. And Reinhardt, you maybe want to say which ones we want to throw out as a starting point for discussion, but this is truly open. So anybody that wants to raise an issue, you're very welcome to. Our job is primarily to make sure people don't speak too long and that everybody gets a chance to have some say in a particular topic. So Reinhardt, you want to just toss out a few things and we'll begin?
Well, it seems to me one pretty obvious one is the quenching issue, which we could debate since there are some, say, extreme views which have been voiced, which we can make even more extreme. I'll try that in a second. Another one was the role of dust, because I think that's something which inevitably we'll have to face as we have higher resolution observations, and of course the IMF variations. I mean, that's a given.
Yes. So we're open now. I think what we'll do is I control this side of the room. Reinhardt's on the other side. We'll probably swap off in terms of people being able to speak. So raise your hand if you like to start with any of those topics.
Why don't we do the following thing? So on the quenching, you see, let's go back 10, 15 years. That's when observationally, at least as I recall, for the first time, more detailed quantitative information on the numbers of galaxies as a function of mass and redshift were known. So from then on, the theorists had to not only explain something at redshift 0, with all these twiddles and so forth, but now they also had to, for the first time, look at the mass functions. And that's when, I think, as I see it, everyone got into a lot of trouble with the recipes at the time, which had in it all the good things like hot halo transitions and so forth, because there weren't enough high mass galaxies around at high redshift. So what people did was to twiddle their knobs such that there were more star formation at high redshift going into high mass star galaxies, and then twiddle even more so that they wouldn't grow further, and that's the AGN feedback in both forms, the radio mode and the quasar mode. So here's the challenge. As I heard, there was some discussion here, and in fact, based on some of the other things we heard, that people are now challenging the challenge. So, to the theorist, suppose we switch off, from now on, AGN feedback. And let's start with the quasar mode. Sorry guys, no more quasar mode. You have trouble?
You don't need the quasar mode. You don't need the quasar mode.
You don't need the quasar mode. Well, okay, now.
I assume all of us agree on this, right? That's great. That us observers can then forget about looking at the quasars for a while.
No more quasar mode? All right, now however, we have these chaps here in the lower half here telling us all about this compaction and so forth. The stuff is coming into the center. How do you get it out again without quasar mode?
But well, so this is kind of on this issue because Marcella Carollo and Simon Lilly aren't here, but I figured I should attempt to defend their honor. So they wrote this paper, I guess a few months ago or whatever, put it on archive. And so the basic premise of this is that they saw no particular need for galaxies to get particularly smaller in size on becoming quiescent, and that instead just the things that become quiescent did so at earlier times. Galaxies were smaller at earlier times. If they preserve their sizes, you can do much to quantitatively reasonably well describe the evolution in quiescent galaxy size as a function of redshift. So simply the act of it having been an ancient galaxy that became quiescent is enough to explain that, oh yeah, they have smaller sizes. And so this is kind of...
It's a slightly different
they would
tack,
argue that
but
They would argue that that compaction is not necessarily something that one needs to do. Now, I understand that this is going to be a discussion topic, but I did want to put that out there, that they've thought about that quite carefully, and it seems not unreasonable that we should at least be thinking about that when we're thinking about the evolution of the population, because it changes with time.
you see, everyone gets about 35 to 60 seconds to talk.
35 is enough.
Yeah, but for the entire discussion.
So, in the simulation I showed today, there was no quasar mode at all. The gas that compactified in this very short-term event, half was consumed into stars, and half was supernova driven outwards. And you're left with a blue nugget, it becomes a red nugget, and then more gas come in. Then
the other stuff which is coming in?
it's coming in, and then you made it AGN radio mode, a kind of wicker AGN feedback.
Radio. I mean, this is
Well, the outflows that you see. I finished my 35 seconds.
You came to the most difficult questions and say no, no, no.
Yeah, just a comment is that the simulations that you're using for these blue nuggets, I think it's fair to say that they form too many stars at redshift, 2, 3, 1. So that's probably part of the, and most of those stars are probably forming in the bulges. So I think that the blue nugget picture probably occurs, but I think the simulations that we're using are probably overestimating the compaction. Factor of 4, too many stars.
Not really. We are consistent with
Factor
abundant
4.
matching within the scatter. They're within the scatter.
I think it's very interesting to see this compaction picture give you a very high baryon to dark matter ratio after compaction happens. And if I understand this picture correctly, this is the leading galaxy from star forming to be quenched. So I guess an interesting question to ask, probably just to look at the morphology and the kinematics of those compacted nuggets, because as in the morning Reinhard showed, those galaxies presumably have actually rotating disks, and whether this is consistent with the simulation and the general picture of this compaction.
If we would have a statistically significant unbiased sample, which is an observational problem, then you would expect if the disk scale length or the scale length of a galaxy just measures the lambda distribution, that you get a Gaussian distribution of disk scale length mimicking the Gaussian distribution of lambdas, which you expect. If you now have compaction, then you should see a second peak with very small scale lengths, because you basically have a sample of galaxies where you remove the angular momentum and you make them more compact. So you should see a double peak. And I'm not sure if that would be seen, which is contradicting the Gaussian lambda distribution, then clearly you have a sample of galaxies that have strongly lost angular momentum, and that would be a clear signature of compaction to me.
Okay, now can I go back to our question? So we've now eliminated quasar mode. Happily, we all are smiling. Let's.
It's great to hear a solution, right?
No.
Have to go out and get some lambda.
Shall we next go one step further and eliminate the radio mode? No.
I mean, you can't keep something quenched without the radio mode, because even if the cooling times of the halo out near the shock are long, you still have short cooling times in the center, and you'll get a cooling flow. So you have to, if you want to keep star formation off for any length of time, you have to have a radio mode.
Andre.
So in addition to cooling of the gas, you also have in situ stellar mass loads that would be building up and would, within a few billion years, would provide full ISM for continuous star formation. But there was some discussion of this earlier yesterday, but I was wondering because nobody really in galaxy formation simulation includes properly sweeping of the gas due to Type 1a supernovae. And I understand that there are comments that Type 1a are not enough, but personally, I don't understand why. Why is not enough? Because energetically, I think they do have enough energy to drive the gas. So couldn't Type 1a supernovae maintain quiescence in ellipticals?
Oh, he has another 15 seconds, yeah.
So I'm a little confused, Reinhard, because you're the one who is finding nuclear outflows from IGNs. So why don't you expect these to play as a feedback agent to quench star formation? My belief is that once you have a hot halo and a massive halo, it will respond to any kind of outflows or radiation or anything that will couple to it and quench inflow.
Yeah, I was impressed by my own findings too. But yeah, well, I mean, in conjunction, I should say, with the radial conveyor belt. Because if you don't move the gas close to the AGN, then of course you have the trouble that you have your AGN in the center trying to do its outflows, and most of the mass is out there at a solid angle dislodged, right? And I don't understand how that goes. So the moving the gas inwards helps, but still, I mean, I was impressed by the arguments of Lilly on the one hand and van Dokkum. So let's pursue this just a little further. Andre, unless you...
Yeah, I was just proposing Type 1a as an alternative to radio mode feedback.
The what?
Type 1a supernovae as an alternative for maintenance.
Yeah. Look, let's give up. I won't challenge the radio mode, but let's go back to, however, so we have no more quasar mode, so that means at high redshift and mid-mass, now we have to get the gas, stop it from coming in, right? So we have, of course, the tool, which is the halo transition. And that is the core of the argument of van Dokkum, for instance, and the fact that the transition line, the quenching line is so steep. And that could be sigma equals constant, and that, to me, makes a plausible connection between where it's actually measured, which is at a few kiloparsecs, and where it happens, which is at 100 kiloparsecs. But otherwise, how should that be connected? Because, what does the central bulge know about, 100 kiloparsecs other than the rotation curve? But now, if the transition of the halo is the agent, and that's a cooling transition, why is the Schechter mass constant with redshift? Which is what Simon Lilly also tells us. Because the mass of the halo, which cools, should go like 1 plus z to the 3 halves, minus 3 halves.
But the halo continues to grow, and it's hot. It doesn't allow anything to come in.
No, but
Well, in fact, I want to refer you to a nice plot that Peter Beruzzi showed. I don't know if he's still here. No? He left? So he showed exactly what, I'm sorry to say, I predicted 10 years ago, namely that at redshift 0,
By you.
the upper limit for star formation is 10 to the 12 solar mass in halo, and redshift 1 and 2, it's getting higher, because you can have these cold streams, and this was presumably based on observations, with all this modest matching and all this modeling. But it looks very consistent with what you want, that you have an upper limit, and always the peak of star formation is in halos of 10 to the 12 solar mass, if they exist.
I would like to have a good discussion of this, because, the 1 plus z to the 3 halves over a redshift range from 0 to 3 is a factor of 8. Okay, so, and Lilly tells us, or at least Peng et al. Tell us that the Schechter mass in both the dead systems as well as the star forming systems are sort of same to within 20% over the entire range. No comment?
say it again?
So I think this has been shown by several people, but if you look at the dark matter mass within a fixed radius, say 50 kpc or 100 kpc, that's fixed basically with time. And so the fact that helium may be growing, but most of the mass is being added at very large radii. So in one sense, if the stellar mass...
So the stopping is not done at the virial rate.
Yeah. Yeah, I'm not sure. Okay.
Doesn't evolve much.
I'm finished.
Anybody boring about quenching? Anything you wanted to know?
Why don't we move on to your second topic, unless someone else wants to comment on this one. Yeah, dust. I think there's a vote for dust. You want to say something about it? No?
I think I used my 35 seconds.
Oh, was that 35 seconds total for the whole session? He's the enforcer,
come on,
the Terminator.
No.
No, this is a different topic. I think you're free to say.
But- No, so the point that you made about dust, I mean, it's really, really important. Just the radiator transfer totally screws up the relationship between any kind of reddening that you see or any kind of wavelength dependence of dust, including continuum versus line, and the total amount of attenuation that's actually there. And I think it was Tadaki, is that right? But there's some more recent results that show very infrared bright cores with ALMA imaging.
Yeah, I mean,
in just some star-forming main sequence galaxies.
There's currently 2 papers.
Right.
One is out, Barrow, with 6 objects, and then the Tadaki paper is about to come out with 12. So this has to grow and will grow. Eventually, I'm sure, as a larger sample will be given once the ALMA-TAC comes to its senses. But you know, I think that will be shown, and I'm fairly sure you'll see these central starbursts. I mean, it would be. But I mean, to remind people in the local universe, the so-called ultra-luminous infrared galaxies, which put out between 95 and 99.9% of its luminosity in the far infrared, of course, have been observed at length in the optical. And without exception, if you analyze the optical spectra, what you'll find are post-starburst galaxies. The riddle also, you know, another way of putting this is M82, the first starburst galaxy, optical and UV observers would always insist on it has nothing to do with star formation. There is no star formation, not much anyhow. So what that tells you is there is no way you can tell from the spectra when you de-extinct it that there is a hidden, very powerful source. That much extinction is in front of it. So that's the regime of the ULARGs. And so the same kind of column densities will be present once you compact the gas into a reasonable volume. It doesn't even have to be a kiloparsec at high redshift because there's so much gas there. So there could be a lot of hidden stuff there, which we don't know about yet.
I'd like to challenge the theorists, and that is, are there any simulations right now that the theorists would say are pretty good in predicting what we should really see when dust is properly included? I mean, I know that we have sunrise, but I don't know if sunrise gives these extreme extinctions, and I think we had trouble trying to match the... Yeah. Okay. So, Joe, you're basically saying that the theorists cannot do what we need.
No. There's a standard way of doing that, and you have to do it with diffusion. And then you have to transition to ray tracing once the extinction becomes, factors of a few. And we had intended to build that into Sunrise, but Patrick Janssen left the field before that ever got done, sadly.
So we need some young theorists to do what Joel says can be done. So that'd be great, because it's obviously going to be an issue as we get more and more detailed observations.
But isn't that a sort of orthogonal issue? I thought you were asking about actually predicting the abundance of dust in the first place, which, as I understand it, not having worked in this field at all, that we don't even know where the dust is, really. We tend to make pretty simplistic assumptions about that.
Any other comments about dust? And I mean, we saw fascinating data about the. Oh, there we go.
So I hate to. We should be constructive about kind of forward-looking about this problem. And so one can kind of throw stones at it's all kind of a mess with the optical UV, but I mean, so almost clearly one way forwards. Has anyone thought about JWST? Longer wavelength imaging is
Not high
potentially
enough.
way forward.
Not high enough resolution.
I was concerned that was potentially.
It's the interferometers period. Now,
So what other are there other observational diagnostics that folks here are thinking about using that would help solve this problem?
We have it. Now, here's the challenge. Who in this room is a millimeter and infrared astronomer? Jonathan is, and he's a theorist. One. Okay? And you go to a submillimeter infrared observers conference, even an extragalactic one, and I have to question, who of you is a theorist in galaxy evolution? You'll get about the same fraction. These two communities traditionally have been totally disjunct, and in particular, unfortunately, the millimeter, submillimeter, far infrared community doesn't know what you're worried about. And so they're all into getting weird objects and the highest redshift right now and beautiful lines and all this kind of stuff. If you go to the TAC, that's why I said that comes to its senses. It says a real crisis at ALMA. If you go to the ALMA TAC and propose for a sample of 100 objects, sampling, reasonably well the main sequence at some redshift, and you come up with your cost accounting, they throw you out. Okay, so that is the challenge. The challenge is to get the two communities together. Maybe, in fact, with all these conferences on galaxy evolution, as we have it here very successfully, it would be good to bring in carefully a new generation of young, long wavelength people in there and teach them that they have to listen to you guys and see what the problems are.
Well, I can make a contribution here. I just got a notice that the ALMA will have a workshop near Palm Springs at Indian Wells. The young people get half of their lodging paid for, and you have till the 22nd of this month to sign up. And if you're anywhere near California, Arizona, there's an opportunity for some of you theorists and observers to go and contribute what Reinhardt's telling us we should do, is that have some exchange between the two communities. Highly encouraged. And of course, next year the organizers will obviously have to invite a few of those from the other side so they can hear, especially the ones on the TAC. Any other comments for the extinction issue? We have a few more minutes. Do you want to?
Okay, IMF. Look, a few years ago, 2010, we had a very nice review article on the state of the art in Bastian et al. In annual reviews, which I thought was a beautiful piece of work because it really put everything together in a reasonably fair way, and you can summarize everything with the possible exception of the central 1 parsec around a black hole in the galactic center. The IMF is pretty much the same. Everywhere where it isn't, it's sampling variations, evolutionary variations, etc. But there is no intrinsic strong piece of evidence for variations. Now today we heard, I forget, was it you, made the argument, well, okay, that's because the environments weren't probed, which are now probed in extragalactic contexts. Bullshit. If you go to, extreme H2 regions in the Milky Way, or super starbursts in nearby galaxies, or the LMC and the SMC, you have a pretty good range of, densities and pressures which would have been there at high redshift. And we have no evidence that at galactic scales, the galaxy star formation process is all that different. At least not in the non-starbursty environment. So can we discuss how safe our conclusion is now that from two pieces of evidence, the spectra of ellipticals and the basic analysis of their mass distributions, that we really must have a variation in the IMF.
What about the galactic center?
That's pretty safe.
The galactic center is different?
Yeah, that's safe, and the answer to that is it's a totally different way of star formation because it's two-dimensional. Your lame duck gas has to go around in circles, and then it can do what in planetary formation happens. You can gobble up the Hill sphere, and so you can grow to very large masses.
I hate to do this. I'm sorry, I hate to do this. I'm not a believer in a changing IMF, in part because it would be truly inconvenient.
Yes.
So just to make my priors completely visible to everybody. That having been said, I mean, so the dynamical part of the mass to light ratio variation has been seen for decades and decades and decades. And that has been interpreted as super old stellar populations, like back before I was a boy. And then when the age of the universe became a problem, then it was interpreted in terms of dark matter, and now it's being interpreted in terms of IMF. So that evidence is safe. It hasn't gone away, but the interpretation was always unclear. To me, the part that's still puzzling is the stellar population interpretation. That it does, I mean, the spectra are genuinely puzzling, but I've always, the concern in the back of, and I can't see anything obviously wrong with the way it's being interpreted now. But the thing that always worries me is that these are stars for which we have no template spectra, right? So the systems that look different are stars for which we have no local Milky Way template spectra. And so then we don't exactly know what the spectra should look like. So we extrapolate our models into that space, but I don't know how well they do. So this is my kind of long, if there's a hole in the argument, I suspect that's where it is. But I don't see anything obviously wrong with the stellar pops angle, sadly. I'd like to see that, but.
Rebuttal?
Trying to move away from models, trying just to compare indices. For example, we find a really strong correlation between, we find the values of the strong IMF indicators, they are way away from the models with an IMF. They are way, you cannot claim that this is, for example, titanium abundances in the case of this titanium molecular band. The abundances that you require to match the strength of the indices is crazy. It's like more than 1 to get the values that we observe in massive galaxies. So abundances is not there's no way you can match that with abundances. And when you combine this is with just one index, but when you combine two indices, for example, the Tio 1 and the Tio 2, these are the two, one of the two indices we're using. They depend in a different way on the IMF and on the abundance. So you don't have room to just say, okay, let's put titanium on our galaxy and you will match the values that we're observing. There is no way. If we are not observing the IMF variation, it's something that really looks like IMF variations. That's, I think, the most we can say at this point.
No, the work which was done, of course, is excellent work, and the proponents are excellent, but there are, I hear in the background, mumbling people. And so I think the thing I'm worried about, not only is it inconvenient, it potentially is dangerous in the sense that it creates sort of a paradigm shift, where then everyone, not knowing what the details are, sort of moves over, and then it can be a red herring kind of a story, where all of a sudden you're chasing down a wrong part of the avenue. So it seems to me this is such an important part of our avenue. And if you believe my argument that the range of environments is there locally, then it would seem efforts worthwhile to try very hard in environments which come as close as they should be, presumably low mass, low metallicity, to see whether the local IMF variations are there. Just do a hard look at that.
Yeah, so just a comment. So theoretically, there is a number of papers published on trying to explain variation. And the arguments were that it's not the local environment that matters, but the global galactic environment. And that is different when these early type galaxies
And you
formed.
understand that?
I understand one class of models which argue that when the environments are much more turbulent, the PDF is much wider, and then there is.
Okay, but these exist too in mergers.
Yes, right.
So, I mean, it seems to me, I cannot believe that we don't have some laboratories locally where we can go ahead and, I mean, for me, the most stunning sort of part of this sort of Bastian et al. Story was the superstar clusters. I mean, superstar clusters are being basically molecular cloud masses being compressed to 1 parsec. Damn it! I mean, how much more extreme can you become in a local environment, which you would think happens in a high redshift universe? And the fact that, despite a lot of effort of 10 years, nobody found any fantastic, consistent variations there compared to the Jabri IMF. Mm-hmm.
Okay.
IMF is in each one is the same, how you can compute the effects of the feedback.
This is the first week where we discussed self-interacting dark matter.
Yeah.
You would have liked that.
I would have liked that. Yeah. Well, would you agree with me that paradigmatic effects should be avoided if one can? I mean, and then I don't take a position other than it should be done carefully and not let's all run over to this side and then in 10, 15 years you'll experience that everyone is running to another side. Okay, should we?
Yeah, I think it's time to close up. I think people must be getting hungry for dinner. Let's thank everybody who gave the talk and the discussion. Thanks. And Joel, any announcements?